Solid edge with synchronous technology extends the power of synchronous modeling to the process-specific environment of sheet metal design. Here we're going to be designing a cover to go over the pulley. We'll start by in-place activating into a part that we've already started. This was just to position the part. So let's start by sketching a rectangle. Using the option for rectangle by center, we can specify the width, the height, and the angle. With grab and go tools, we can quickly turn that sketch into a tab using its region. The thickness of material is set in the material table. Here we can set the type of material. In this case, we're using steel. We're going to set the thickness by a gauge. Each gauge has a specified thickness. So we're going to change it to 14 gauge. When we apply that to the model, you'll see the thickness change. Again, using grab and go tools, we can easily select the 3 thickness faces and drag them into flanges simultaneously. Solid edge determines which flange should contain the bend relief automatically. Next, we'll sketch a circle on the top of the flange, or the top of the tab, I should say. We're going to use this to create a dimple, which is a process-specific procedural feature. All we need to do is select the region and give it a direction. Now we're going to add PMI dimensions. Notice as we add the PMI dimensions that Smart Dimensions automatically finds the theoretical intersection of the bends to give the true outside dimension, even though we only selected the edge of the bend. With synchronous technology, we're not limited to only specifying the overall outside dimension like other CAD systems, but instead we can drive our design by either specifying the outside or the inside dimension for a sheet metal part. Notice as we change the inside dimension, the outside dimension changes based on the thickness. To fix our interference problem, we can add another process-specific feature of a jog to our part. To create a jog, we simply sketch a line and then run the jog command and specify which side of the material we wish to jog. We can jog it inside or we can jog it outside by just positioning the cursor. The power of synchronous modeling enables us to select the jog face and using the powerful steering wheel tool, rotate the face into position. Next we're going to fill this small gap in the back. So just selecting the edge and dragging, we can create a small flange. Just a few mouse clicks, we can define that the 2 faces are to be coplanar. By offsetting the steering wheel tool from the thickness face 1 mm, we can establish a 1 mm gap between the 2 thickness faces by selecting a key point during the drag edit of the thickness face. Next we'll create 2 flanges on each side. Notice how we can drag them simultaneously using the grab and go tools. Again, we can use the same technique as before to relate the thickness face to be coplanar with the flange face. By locking the dimension to the flange, we can preserve its width as we rotate the side face. So as we start to rotate, notice that the locked dimension maintains that width for the flange. Next we need to create holes in our part to create clearance for the bolts. Using the project to sketch command, we can specify an offset from the diameter of our bolt to create clearance. In this case, we're just going to offset it 0.5 millimeter. And we're going to do that on the other side as well. By By sketching these two circles, this creates regions that we can use to create holes in our part. Once we have a region selected, it's simply a matter of just dragging them through or specifying which direction we wish to create the hole. In this case, we're going to go through all. We can also use dimensions to control our part as well. So in this case, we're going to add a height dimension, and depending on which way the arrow is pointing, which face is going to get moved during the edit of the dimension. In this case, as we change that dimension, you can see that the top will rise and fall. In this case, we're going to pull it down. Next, we'll switch the direction of the dimension, and now we'll be pushing the bottom face up or down. In this case, we're going to push it down. This kind of on-the-fly editing flexibility is not possible in a history-based system. We're going to add some more clearance again for the pulley system just by rotating the side flange. The steering wheel can also be used on a thickness face to rotate it into a new position. Next, we need to cut away part of the pulley cover. When locking to a plane to create a sketch, notice how we can choose which edge we wish to align the X and Y directions to. Creating a closed sketch enables us to drag the interior regions to completely cut through our part to remove unwanted material. In this case, we're using the through all function, and we're going to select to cut through both directions. Because the dimple is a procedural feature, we can edit its profile to drastically change its shape. In this case, we're going to completely delete the original sketch, and then what we're going to do is project edges of the belt to define the shape of the new dimple. Rotating the model into position allows us to easily select the edges of the belt. And as you can see, it gets projected up onto the top of the tab in the sheet metal part. And this becomes our new profile. Notice this is an open profile. So once we accept, we need to tell it which way to make the enclosed volume. In this case, to the inside. And we can also change the height of the dimple. This is going to give us more clearance on the pulley shaft. Next, we'd like to create an etch feature on the top of the sheet metal pulley cover. To do that, we first define a text sketch. In this case, we want to etch not a step into the top of the sheet metal part. Once we have the text defined, we can use the N key to determine which edge we want to align the text with. Once we have a sketch placed, then we can use the etch command to actually etch this into the sheet metal part. Once we have a 3D sheet metal model, we need to show this in the flattened state for manufacturing. Solid Edge is able to easily flatten this complex sheet metal part and even give us the overall size we need to order stock to build this part. We can even control how the foreign features look in the flattened state. As we return to the bent state of the model, we need to add a bend table. Solid Edge automatically generates a bend table, which allows us to specify the order in which bend should be placed during manufacturing. The table of information is exactly what the manufacturer will need to actually build this part. As we move this bend up the tree, notice the balloon changes. Next, we're going to use a quick sheet to create a drawing of our pulley cover. Quick sheets enable us to lay out views very quickly for common parts. In this case, it has a predefined flattened view as well as an isometric view to help the manufacturer visualize the finished product. We're going to use coordinate dimensioning, and as we continue to select points along the model, you can see how the coordinate dimension is automatically generated and the position is even specified, placed based on our cursor position. We can do this in the X and the Y directions. If we're creating a dimension that's very close to another one, we can create a jog in the dimension just by simply clicking, holding the Alt key, and create a jog in our coordinate dimension. Adding the bend table that we created in the 3D completes the loop to manufacturing. In the bend table, we can specify a title. In this case, it's the IronEagle's pulley cover. We can control exactly how this is going to look once it's placed on the drawing, including the font and the style. We can also specify what's going to be in the callout for each bend. In this case, the bend sequence and the bend direction. As we zoom in close, you can see the bend table is exactly what we specified in the 3D model. We have complete control over our bend table properties. For instance, if we want to combine columns that have similar entries. Solid Edge with synchronous technology enables us to create highly editable, complex sheet metal parts quickly and easily. And just like synchronous part modeling, edits can be made quickly and easily without fear of downstream features failing due to history in the model. We'll save our draft file, and then we'll return back to the 3D model. As we close and return, you can see this in the context of the overall assembly.